Wolfgang Reisig again here and tell us a little bit about the fundamentals. So please go ahead.
Okay, good morning ladies and gentlemen, and hello to the millions of listeners and people who will look to this video at the end, which is recorded with this camera. You should not forget them. So in 100 years we'll still be interested in what we have done here. Okay. So I'm not sure if I can give you some useful information on this topic. It's more a set of questions than a set of solutions. So what could be the foundations of service-oriented computing? Why is it needed? If something like this is needed at all, what could it be? We are so wonderfully progressing without such a thing. So we see very impressive talks in this conference which make new things and more and more new things every day. And anyway, there is this deep theoretical informatics stuff that we all had to learn and frequently didn't like so much. So that's enough of theory. Why do we need something else? This is, say, the background questions of this talk. So why is it needed? Of course, it's needed to make this field conceptually simpler. Because it's, I think, in some parts amazingly difficult. And intuitively, I even think, I'm not making friends this morning, very many, unnecessarily difficult. It should be simpler, but we don't know how to make it simpler. If it would be conceptually simpler, then we could teach it better. And I confess I have always problems to teach this kind of stuff, because it's so intuitively unnecessarily complicated. And if it would be conceptually simpler, it could be better usable by non-experts. Because, don't need to go into detail there. What could it be? Don't know. We should, as a principle how to proceed, should identify the fundamental concepts. I think we don't know yet what the fundamental concepts are in this field. And then build a theory on top of this. That's our task to do. Okay. And we are so wonderfully progressing without, yes, it is true, for a while we do so. But I'm not sure if we will do so another 10 years or 20 years. Or you will do, I'm not sure if I will join you in this enterprise. Okay, and this theoretical informatics stuff, so there's so much on formal languages and automata and logic and complexity theory, but I think what we need is something fundamentally new. And I will also expand on this a little. Okay. So my first part will be to show you that service-oriented computing, or call it however you want to do, substantially exceeds classical theoretical informatics. That will be my first topic. And my second topic will be the central part of services is that they are composed. So composition of services is the crucial point. The third one is we want to compose many services. So in this area of theoretical foundations, we have a lot of papers that compose two services. So composing two is fine, but we want to compose many usually, and I will show you how this could be done. Fourth point is composition should retain or guarantee some properties. So if you have two components that have certain properties and you compose them, then by definition or by construction or by theorem, it should be clear that the composed system has maybe the same or some other relevant properties, such that you don't have to prove the properties for the composed system. And finally, the kind of composition I'll show you is very expressive. So I'm always impressed by myself how expressive this composition is. Okay, so let's start with the first point. Concerning classical theoretical informatics, this is very dangerous here.
Yes.
I should not
There's
go
another one.
up and down. Okay. So let's start very fundamentally. And if we want to make informatics a science, which we didn't do so far, I think, then we should look to other sciences and look what they do. And the example of a science is physics. So what is physics? It's a system of notations and relations among the notations, stating laws of nature, and of course we don't have laws of nature, but something other, something else. And all this is described in terms of models. So my central points are two. One is what corresponds to the laws of nature, that is the properties, and the notion of a model should be considered much more relevant than we do it so far. Okay. And I will give you some examples about models in physics or in theoretical ways. And I think the term energy is a very interesting notion, because in nature there is not something like energy. In nature you have a lot of phenomena, but you don't have the notion of energy. The notion of energy is an abstraction from many different aspects. And still, I think everybody of us has an intuitive, very nice notion of what energy is. We can even accept that there is a quantification of it. We could say there's a certain amount of energy in say, electrical energy here and heat energy there, and somehow we are even accepting that they correspond to each other. So energy is a very difficult notion, much more difficult notion than what we have in informatics, but still it's very intuitive. And so the question is, what is the trick, so to speak? What do these engineers do to make such complicated but yet intuitive notions? And the point there is that they are intended to describe invariance. So my first point here will be the notion to show you how important it is to consider invariance, not only in physics but also in informatics. And we will consider invariance in informatics. But let's go back to the question of invariance in the context of energy. So assume you have a car, it's over there, and it's stationary, then you speed up, and then after a while you crash into something else. So what had happened? A lot of things happened, but something remains. And the notion of invariant is that what remains. So what remains constant when you do this short drive? So this is the notion of energy. First it is in the gasoline. So the car is standing there, and in the gasoline is a lot of energy. Then you transform the energy into acceleration, and at the end you transform it into deformed metal sheets. But we all accept that the amount of something that we call energy remains constant in this process. And I think we understand the process or dynamic behavior. We understand properly only if we know the invariance of the behavior. And that is what we also should make in informatics. So what they really did, the physicists really did, they searched the notion general enough to describe what remains invariant in such a process. And they identified this, and it took decades to identify this, and then they called this energy. And therefore we have now this beautiful notion where we can compare electricity with heat or with gasoline. Okay? So that is invariance in physics. And scientific theorists physicists accept intuitively hard models, which they call theories, and mathematically they are really hard, as long as they offer convincing explanations and in particular invariance. And likewise in chemistry we have this kind of processes. We say if we have this stuff, then something can happen, and we come to this stuff. But also here the whole amount of stuff retains. There's nothing coming new, there's nothing going out. This overall sum of material retains, is only transformed. And we also make transformations. We make digital transformations. And I ask myself, what is, if there is transformed so much? On Sunday we had a talk here, everything is new, we process, we do something, everything new is produced. No, nothing new is produced. Something is transformed. And we must understand much better what is constant during a transformation. Okay. So search for good models means search for comprehensive invariance. And I was impressed some time ago, but this is, I should say, the most famous invariant by Einstein is this one, which all we know. And some years ago I got involved in something that's called theoretical biology. And in theoretical biology or constructive biology, they start, so far they had differential equations to explain their stuff. And slowly they move away and they do it with petronets. And there I became involved. And I asked them, why do you do it now in petronets? And they said the main reason is that they want to see the invariance better. So if you have a process, a biological process of metabolism, so something is changed in your body, so you eat something and then you change. But at the end, the sum of what goes in and what goes out, the sum remains constant. Okay? And if something was in and went out, then you retain also the state. And this kind of assurances that your model seems to be really correct is that you compute all the invariants. And if the system is not covered by invariants, or if the system model, I should say, is not covered by invariants, then it's more or less clear that you have made a mistake. And that is the reason for the theoretical biologists to consider this kind of patronage, because they give them a calculus to compute invariants. Okay, for us here, we have this is a little bit my last example. For us here, it is the so-called Frank invariant. And now I'll tell you what the Frank invariant is. So we have seen the Einstein invariant, we have seen already. So the Frank invariant is the following. The sum of the length of his hair remains invariant. Okay? And to make it clear what it is, so when he was young, he had very, very many hairs, and they were very, very small. Okay? And this is what we have now, is the number of hairs significantly decreased, but the length increased, so again the sum of the length is invariant. Okay? And so let's now look to the future and something like this. So there's one hair, and that's very, very long. Okay? So I'm sure that you will never forget what an invariant is. Okay. That took me almost 1 hour to make. Okay, so our task is we must develop integrated concepts and theoretical models in the style of exact sciences. And for what? And the problem is we don't even have a notion for what. Is it information? Is it data? We don't know yet, and we don't have a word for it. And so I will not put here a word, because then you complain that my word is wrong. And certainly it is wrong, because as long as you don't have an intuition what you want to say, you don't have a word for this. So maybe you find one, and then I would be happy. So what should this do? This should support non-trivial analysis and verification by help of invariants. And now let's look at models and invariants in informatics. Informatics has a lot of models, you know them all, and some of the models have also invariants. For instance, Hall logic for programming offers you some invariants, while compared with invariants of physics or biology, these are really trivial invariants. There's not very deep theory behind, a little bit of logic, that's it. Okay, so I would like to see the notion of invariance when you use a cash machine. So what remains invariant when you use a cash machine? Of course it is the numbers on the money on your account and the money you get in your hand. So before you have a lot of money in your account and nothing in your hand, and at the end you have some money on your hands and less money on your account. And the sum of money should remain invariant. Okay. And also the process, there is an intermediate process that should retain the amount of money that is going through the system.
But this invariant is given by the application, yeah? Or by the domain.
Of course, yeah. Yeah. There is, I don't want to say that is a general notion, not at all. So in this domain, we would like to see this kind of invariant. And if you build a system for the banks, you should be able to prove that your system does not produce money and does not waste away money. So this would be, so to speak, a more high-level invariant. Or for instance, I'm always asking myself, what remains invariant if your computer runs garbage collection? So you don't put something in, you don't get anything out. It does some internal reorganization. And of course, as long as there's not going something in or out, something retains invariant. So what is it that retains invariant? So we need a notion for that, what retains invariant. which we don't have so far. What retains invariant if we fulfill a contract? Also there's something that should be invariant. Okay, how can we achieve all this? Of course by means of
Take a look at the hairs.
What?
Take a look at the hairs.
So it's not young anymore.
So that is from 2004. You see, I haven't seen him in the last years, so maybe now he looks a bit different. Yeah, so Grady Butch, one of the founders of the modeling tool of UML, says we must do it by means of models. We must alleviate models to a first-class citizenship, a peer of traditional text languages, and potentially its master. So I'm not happy that I see so many programming stuff in this conference. I would love to see much more modeling stuff. Okay? So please next year speak about models and not about programs. And I'm happy that Sharon is coming. And I'm sorry, Sharon, that you missed the first 5 minutes, that you would have had more fun. Okay. So what is the fundamental difference between modeling and programming? And you should keep this in mind. A model behavior is not necessarily implemented. So we have some services that we never intend to be implemented. Still, these are services. And in the context of implemented programs...
But isn't the goal that the model is what gets executed?
You can model behavior.
Yeah, and so Shreya has shown the sequence diagram, and you can execute the sequence diagram. You just provide a model and it gets executed. So it's only a level of abstraction, isn't it? Yeah, this is a serious question. Okay. Again, finally, the goal of UML is also to be executed.
To execute is something else. I want to represent a kind of behavior.
Wouldn't it be excellent if that what you represented already has an operational semantics?
Yes, it frequently yes, and then it can, I wouldn't say execute, I would say simulate. Because say if your model describes how to cook a fish, then to execute means to cook the fish. Yes. But what you mean is to simulate the execution of the fish on your computer. That's the difference. And the difference is that at the end, either you have a fish to eat or you don't. I prefer not to simulate, but to do it.
But again, there are models that don't have real-world counterparts, right? If you invoke services, blah, 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 you start a BTMN model, right? So there are models that do not represent physical processes, right? But like a program, you describe, I deduct your account, I increase my account, there is no physical notion what an account is. And
for me, an account is a physical, is an item of our reality. Absolutely. We are in a world where accounts are real items, first-class citizens.
To agree, yes. Yeah. But it's different like fish. So what I want to say is, so from my perspective, yes, we need to model, but not only for abstraction, but also for execution. I think it's ideal if you raise the level of abstraction, you become more easier. This is your go-to, but it's kind of invariant. And then the idea case is that you execute what you have modeled, what end users, what domain experts can basically do.
Okay, and the second point, I think you said it already, is the modeler freely chooses the level of abstraction, whereas in programming you usually get a fixed level of abstraction in the programming language that you have to use.
Although the programming language is also an abstraction for the tool regime.
Of course, yes, but usually you are told you have to program in C++ and that's it. That fixes
like
your...
30 years ago, you have been told you have to use assembler. Few people use assembler.
So,
I think that this second one makes the difference.
Because
if you choose a very high level of abstraction, you will not get a model that can be executed in your sense.
Okay.
Also, this is debatable.
No. Abstraction means taking something away, and if you take the information away, what's needed to execute it, then it cannot be executed.
Well, I make a model, very abstract model that allows me to fly to the moon. Okay, and then I execute it, and in the model I say now I'm on the Earth, and then I execute and then I'm in the moon. So I have
yeah, but the model does not contain all the information that is needed to execute.
That is true.
But
Yeah.
Frank talks about models that are somehow complete in that sense that they contain all the information that's needed.
No. This kind of notion of completeness and all information, that is very debatable what it means.
I agree.
Does it mean physical details to the atomic level? Certainly not. So you always have an abstract level in between.
Yes, you do.
Okay. Yeah, so the state of the art in informatics, I think we are by far not on an abstract level enough that we could be compared with Einstein, and I fear we are even not on the level comparable to Newton. At least we should think that there will be something fundamentally better than what we are doing so far. Okay, so let's go into more details. I think there are three fundamental paradigms of programming. The first one is conventional programs, procedural programs, following the input, process, output model. And I have learned that our children still learn in informatics lessons this very simple and I think even wrong kind of model, as if computers behave in this old-fashioned way. Okay, the second paradigm is object orientation, where you have attributes and methods. And I think the third fundamentally new thing is service orientation or components or whatever, and the loose coupling is the fundamental thing. So let's look what are the theoretical foundations of all this. Here we have computable functions, complexity, theory, logic, all the fine and beautiful theoretical informatics stuff. In object orientation, we have abstract data types, algebraic specification, sequences, structures, first order logic. So this is all the fundamentals of object orientation, and the fundamentals of service orientation is nothing. They just did it. Industry did it, and that's it. And industry is not interested in anything like theory, and theoretical people ignored it. So that's the state of the art for the last 15 years. And I would be happy that some of you will join me and try to change this situation. So I will speak about three fundamental aspects to improve this a little bit. So one is communication, one is non-ending behavior, and the third is causality. Okay, so communication. So you have two computers, and the blue one, the left one, sends messages to the right one, and the messages may also disappear, you know, there may be mistakes, and the right one, the red one sends to the blue one, it will also disappear. And the question is, if you have this kind of behavior of lines, how to establish communication, and then we can send acknowledgement and copies, and we have protocols that take care of and recognize and fix lost information. That is a beautiful notion of protocols, and of course that cannot be modeled by a Turing machine, because a Turing machine would abstract away all the communication stuff. A Turing machine is one machine. There are no two Turing machines. So the complexity of this story is not in the computation of the single machines, but in the communication between them. And informatics comprises formal aspects that cannot be explored. This cannot be explained by a computable function from the words of an alphabet to the words of another alphabet. It's simply another word. Okay. Or you can say it this way: if you have two, you need two. You need two, and not one. And the whole phenomena you are interested in cannot be reduced to one, at least two. Okay. So now comes the next, this is the technique called non-ending behavior. And why is it so important? Well, the classical view is terminating behavior is intended. So you have a computer that computes a byte, that computes a result, and when on termination it gives the result. And if it doesn't terminate, it's a mistake. It will not wait forever and there will never come a result. That's the classical view of behavior. So in our world, the service orientation, the systems, they are always on. The cloud doesn't close in the evening and open in the morning. An elevator control runs always, and business informatics also. So the view is that infinite behavior is intended, and finite behavior is a mistake. So just the reverse of the classical view. And how come it? Well, because we have communication while the system is running, and not at the end of the computation, but during computation. Okay, that's here. And how do we cope with this? Well, we have this notion of temporal logic, which you should be aware of. Sometimes we say, from now on, some property Q holds, and that's a typical invariant that we have spoken about here. And if the property is denoted as Q, then we write GQ.
No, this is really invariant. What has been before now?
Okay, before now we don't speak about this things. Then it becomes a little bit more involved. Then it becomes invariant.
Yeah, but really I would question the invariant, because I mean from now on Q holds, and from tomorrow on X holds. Yeah?
No, from now on Q holds means from now on till the end of the days, always.
But is that typical for? I mean, can you give an example for that? I mean, I don't see that this is included in SoC.
For example, what kind of example do you want?
Why is this constituent to service-oriented?
From now on, the service is why. We wanted 7 by 24 and so on. Just forget that you have maintenance.
Okay, that's invariant.
Yes.
I admit I'm speaking now not specifically about service on the computer. My point here was that we have spoken already about invariance. That means something remains invariant for all the rest of the days. But in addition, we need something else. That is, eventually, some other property may hold it. Okay? The two properties we need, they are related to each other. So there's a real logic behind this, and you can have fun in thinking to say it's always the case that P holds is the same as saying it's never the case that eventually not P holds. Okay, so you have a full-fledged logic with very efficient tools, and there is temporal logic. And the reason why we use temporal logic is that we speak about infinite behavior. And why do we speak about infinite behavior? That we talked about because we have interaction during computation. So in this sense, the interaction during computation implies the need for temporal logic.
Just because he doubted that something like the holds forever is realistic, did you think about this to use interval logic? Because you have a release for a certain point in time, would that make sense?
Of course it makes sense. This is a very specialized temporal logic. And I only showed you the fundamentals, the fundamental idea of temporal logic. I wanted to motivate, why do we suddenly speak about temporal logic? So for 40 years, informatics did, not 40 years, that's not true, 20 years did without temporal logic. Suddenly temporal logic is so relevant. Why is it? Because of, we speak about infinite behavior. That was my message here. Okay. Yeah, causal independence. So on Monday we learned about patterns. I think I've forgotten who spoke about patterns. Somebody even spoke about this book here, the book on pattern languages. And I was a bit surprised. I think there is one most fundamental pattern, and this was not mentioned so far. Also on Sunday, somebody spoke about patterns. On Monday, somebody spoke. But nobody did mention what I consider the most fundamental pattern, and that is the beer hall pattern. You know the beer hall pattern?
Sure.
Okay, so the beer hall pattern in this building pattern context, what does it say? It says, describe the behavior that we all know very well and love very well and do it every week. We go to the beer hall, and what do we do here? So I quote from the book, so that people are continuously crisscrossing from one to another to click their glasses. So especially in Munich, in the end of September, you do this all the time for 2 weeks. You go around and click your glasses. And now let's describe this kind of behavior, so in a more formal way. How do we do that? Well, this would be a typical behavior. There's a red person and a green person So the red person goes around and he meets the green person and they click their glasses and then they go around to some other places and then they meet a second time and then they continue the cycle. And assume there are also a brown and a black person and they also sometimes meet and click their glasses. And there may be even more the blue person. And what does he do? He first clicks the glass with the black one and then with the brown one and then with the green one. Okay, so this kind of behavior is going on in a beer hall. So how do we describe this kind of behavior? Well, let's call this clicking A, B, C, D, E, etc. And if you abstract a little bit away from this, what you gain is a partially ordered set of events. This one. So that means first the A clicking is done, then B, then F. And independent of this, first D, then C, then E, then F. Okay, first D, then C, then E, then F. Okay? So, but this is a partial order. There is no order at all, say, between C and A. So you cannot say C was before A or after A. There is no causal relationship between them. So behavior, so far, traditionally, we describe behavior as a sequence of events. And we motivate this that it is happening in time. But there is no notion of time, no reasonable, no useful notion of time in this context. So what is relevant, what constitutes the behavior of the system, is causal dependency. And causal dependency is different from time because this is a more theoretical aspect. If you have a notion, assume a notion of time, then you assume the notion of at the same time. And at the same time is a transitive notion. So if A is at the same time as B and B is at the same time as C, then also A is at the same time as C. But independence, what we have here, so A is independent of B and B is independent of B, but A is very much dependent on B is dependent on A. So the complement of causality is not transitive and much more richer structure than the complement of at the same time. And this kind of behavior is relevant for our world. Okay, causality structure of the world to understand social computing avoids the naive notions of time and of observation. And then also we can learn from physics, they also skip our intuitive notion of time and of observation. Okay. So again, I think I run out of time very much. No. Yeah, but I know what I still want to tell you.
This is the introduction.
Yes, I'm still in the introduction. So, how do we describe this kind of behavior? And I show it to you because it is really interesting. So we have again the blue system, and assume it behaves very simple. It starts in the state and it makes ABC, ABC, nothing else. Okay, we understand this behavior properly. And if you want to describe it in detail, so then we say this is first time A occurs, first time B, first time C, then second time A, B, C, etc. So this is the unfolded behavior of the blue computer. And here the red one, and say the red one does D, E, F in this circle. Okay? And its behavior, of course, is this. So far we understand it is trivial. And now our point is we consider this behavior of the computers, we consider as one behavior. So for me, conceptually, now this is one system. And the simple question is, how does this system behave? Consider it as one system. And what is the usual way to consider this? Well, we say this is a potential behavior of the composed system, but also this is, initially it could start with D, and after the D it could do the circle, or it could continue with E, and do the circle, or it continue to make only this circle, or it could do first this circle, and then this, and then E, and then this. So all the paths through the system, and this is the overall behavior of the composed system. And you see how difficult it starts. And even more you want to say, well, there's some kind of a progress assumption. So it's not intended to say that only the red one makes its circle and the blue one never occurs. So on top of all this, you must assume a notion of that is called fairness. And now things become quite difficult. And if you want to consider the overall behavior...
This was too fast. Why do we need fairness?
But if you want to say the composed system should not, the following behavior is not what you want. Namely, the blue one does nothing, and the red one only continues. And the blue one does nothing. Do you want it? Aha, you don't want it. So you want to exclude a certain number of behaviors that are formally here possible. And to exclude them needs a notion that is called fairness. And this is an extremely difficult notion, and you even cannot implement it. You can implement something more strict, but just to exclude all those notions that were eventually temporal logic, say the blue one does not do anything at all. To exclude this, try to implement it and you will fail. Yeah, you don't believe, but we know. Okay? So now, what did we want to do? We wanted to do something very simple. We wanted to consider the behavior of this system, which consists of two very simple behaviors. We wanted only in our head to consider it as one system, and we run in amazing, stupid problems. And this cannot be a proper theoretical foundation of what we want to say. Okay, and all this is motivated by a notion of observation, which is a difficult and not intuitive notion.
Okay, we say it's difficult. So the upper blue graphs, they are process models, and the graph on the upper right is a choreography. So it is known in SoC, right? In SoC.
What is the choreography?
To describe independent, to describe the behavior of a single service by a business process and orchestration, and you tie together multiple services by the choreography. Basically show how they exchange messages. So this is the concept, isn't it?
This model is even much simpler. I understand.
No, I want to say this is what the service computing guys have recognized, that they need something.
Yeah. Okay. Yeah. So what?
And what you call, please go ahead. Next slide. So the upper models, the cyclic structures, they are models.
Yeah.
And the linear structures are instances. Instances.
Yeah.
Right? If you have a model, you let it run, although you say you don't know execution, then you can trace of what happened based on performing the model. So there's a notion of the model. I agree. Yeah. And what is the abstract formal description of all this? I will show you. This you should consider all on the modeling level. You should consider this as one kind of behavior description. And how do you do it? You make boxes onto these arrows, and then what you get if you put another toe in here, you work a pattern net. Okay? And this pattern net describes exactly what you want to see. Okay. And this now is the two sequences is the behavior, the unique behavior of the system. It's a partial ordered set of event occurrences. This one. Okay. I made a variant which I skipped now. It takes too much time. So summing up, the semantics of representation should be some kind of mathematics, which is not yet the case, and it should be done. Okay. We should spend effort on this. And now comes my second point. And now you understand why I was nervous. Services are made to be composed, and now I think I should go on a little bit more quickly. Now, this is said already, composition should be a simple operation. Composition should, again, so you should be able to compose any kind of services. In principle, you can compose them. It may not make much sense to compose any two services, but in principle, you should be able to do it. There is a famous philosopher, Paul Watzlawick, who said in 1967 already, one cannot not communicate. So if you have two systems that are able to communicate, they will do something with each other. It may be not useful, but something will happen. So they don't interact anymore, and this would be an example. If you say ticketing is the composition of sell tickets and buy tickets. So this is a kind of composition. And description of semantics of composition of services should be done on a high level. So we have a lot of theoretical stuff on a very basic, operationally very basic level, but we should lift it to a higher level, which has not yet been done. And we should describe system properties.
Okay, this was number 2. You see, we proceed to be quicker. Number 3 is we need mechanism to compose many services. So what is the fundamental problem of many services? And I give you an example. This is a supply chain. So you have raw material, you have a machine, you have a factory that supplies, say, steel to the manufacturing company, and they produce, say, spoons, and the spoons are distributed, and you have a customer shop that sells the spoons to the customers, to the consumers. Sorry. Okay. So if all the behaviors of all the components are described as services, we see a service has an interface, and very naturally the interface is partitioned into the right interface and to the left interface. So every component has a right and a left, say, partner here. And they are called in different ways. There may be input and output, or consumer, customer and supplier, provider, requester, producer, consumer, buy side, sell side. It's always very typical that you have the interface partitioned into 2. And the second thing that is so relevant is composition must be associative. So what does it mean? It means when you write just, say, in abstract way, the composition of all these components, then you don't want to make brackets. Then it should be irrelevant if you first compose those 2, and then to the left this one, or if you first compose those 2 and then to this one.
You're looking for atomic notions. Isn't the atomic notion in this context an endpoint that either emits messages or receives messages? That's not the... You can
do this, yeah. You can say, my right partner
sends... The question why I'm asking, because you also said that loose coupling is important. Loose coupling means you asynchronously emit messages and receive messages. So it seems to be because you are looking for the most basic terminology, the notion of a message and asynchronous behavior.
I agree with you. This can be done like this, but it needs not.
You thought about it.
Yeah. Okay. Yeah. Okay. I just wanted to make clear what associativity means by an example. So assume we have a socket and an adapter and a plug. In Britain we have this strange kind of plugs. Then it's not important. You can put the adapter into the socket, and after you have done this, you can put in the plug. But you also put it through the other way around. First, put the plug into the adapter and then altogether into the socket. So that means associativity. And if you have a lot of services, which each with the left and the right partner, and you want to compose them, of course you expect they are associative. But if you do it in a wrong way, and we started to do it in the wrong way, then it turned out not to be associative, and then I think it makes no sense. Okay. So now how can we do this? And now tell me how much time is left. Okay. So I'll give you an idea how you can make a formal system that is, say, associative, and it guarantees that any 2 components can be composed. So this would be a typical component. It has some internal behavior which we are not interested in. It has a left part, the blue is always left, and it is labeled B and D, and has a right part that is right, and it has 2 A labels. 2 A labels. And that is the complicated stuff. So the idea is if you have 2 A labels, you number them. One is number 1 and the other is number 2. Okay. So in a way, every node has its label, and most have number 1. And only if there's a second one with the same label, then it gets number 1. That's the whole point here, and the inner is just kind of a box. So now assume we have another component that looks like this. We have here an A label was number 1 because there is no other A label in the left part. And it's also number 1 and here on the right left. Now the question is how would you compose them? And the idea is very simple. You compose the equally labeled nodes you compose. And if there are many of them, from here is the question, do you compose this node with this one or with this one? Then the answer is very simple. Take the one with the same number. Okay? Sorry. So what you do is, as this you compose them here, and then the question is what is done with this D? The D goes to the left part of the composed system. So D goes over here, and this A goes over there. And then you see that the numbering may change. So here the A had number 2, and now it gets the number 1, because in this part we don't have another A. Okay? That's the whole trick. And the whole point is, if you have this kind of structure, then composition is total, which means any two of this can be composed in a unique way, and this composition is associative. That you have to believe me, because it cost me 3 months to prove that this is really associative. Associativity proofs are always very involved, and it took a little while to make the right choice for cases. Okay, I give you some pictures only. So this is a machine, very simple machine. Behavior of the workflow: you put in some material, you get out the product, and you do this by help of the machine. So initially you have the machine and the material, and at the end you have, of course, the machine back and the product. So now compose 2 of them. So I just draw it a little bit different, so the product goes over here, but it's the same picture. And here again, the same picture, also drawn a little bit different. And what means to compose them? Of course, it means that the machines are glued together, the machine part. Okay? So the name machine disappears, and they get white, and now you compose them, and the resulting system is like this. So again, you have initially the machine and 2 material parts, and at the end, the machine is still available, and you have 2 products. And if you mix 3, then it comes out this way. Okay. So the simple, this kind of composition gives this kind of behavior.
But that does not, I mean, this kind of composition does not help in your nice example of the production chain you had.
Why not?
Because there the product from one service is the material of the other one.
That is just renaming.
Yes, so you have to introduce some
You have to introduce some renaming, yes. Yes, you are right. I consider renaming a trivial information.
Yeah, but you argue on the quality of names, so it's important to have the rename.
Yeah. You should make this rename. Yeah. Okay. Here another example, but I don't go to the details. The producer, a broker, and a client, and the only point here is say, if you compose this with this, you see they negotiate. So they negotiate by telephone, and then they send either the broker either sends reject or he sends an order. And if he sends an order, the producer will ship something, and you see the shipping has no counterpart in the broker, but only in the client. But that works out very nicely. So this would be the composition of producer and broker. And you see now the D part is going to the right interface of this product, and this would be the broker and the client together. And to show you the overall picture, this is composition, producer, broker, client without brackets, because it is associative, and this has been the 3 components, and this is the composed system. And here you see this very naturally composed directly with this without involving the broker. Okay. Now the point number 4, composition must retain or guarantee properties. And here you have an example which I go over through in a very rough way. This is say internet shopping. So you start here, you choose a product, you send an order, you receive the product, and you accept the product, and that's it. And there is this fundamental notion of soundness that has been introduced by Wolfgang Reisig, saying each reasonable workflow is sound. Soundness means you have a unique starting point, a unique stopping point. Each transition that is written down can occur, and you can always reach the final state, and if you reach final state, no litter remains. So say, if you go to a hotel room, you don't want to see anything left by your predecessor. That is the idea of this. And that's soundness. And soundness is a wonderful notion because it is technically not so simple. In order to prove it, you must consider all reachable states, which is complicated stuff. But what we want to do is, of course, to say we start with very small components where you can prove soundness in an easy way. And then we want a composition such that if you compose two sound systems, the compose systems also sound. That's what we want, and that's what we achieve. And I just give you an idea of this. So now here you have the behavior of the buyer, and the buyer, there may be an alternative. If the buyer does not accept the product, he returns the product. So if you have this token running here, it goes either there or it goes there. Okay, this is sound, and there is another aspect. So if you receive the product, then you start a timeout, because you are not allowed to return the product after 3 years. You are only allowed before the timeout goes on. So in the moment this transition occurs, there's a token here as well as here, and this token here retains for a while and then goes to timeout. And if there's not a timeout, you can no longer return the product, but you must keep it. Okay? That's the whole story. That is not sound because of what? Because this situation is reachable. You have accepted already the product, but still the timeout is not yet over. Okay. So now we can add a seller. What does the seller do? He receives an order, he sends the product, and he files a record. And this can, in the pattern, simply be drawn like this. And I don't go into the details. This again is a very nice and sound system. And now comes an interesting point. That is, the following state is reachable. So the buyer is already willing to accept or to return the product, and the seller is waiting, and now the buyer wants to continue. So maybe he wants to continue to buy a second product, but the seller is still waiting for the timeout. So the seller cannot continue here because the timeout has not yet occurred. Still, we want to have a second purchase, and this, now I hope you understand my graphics here. So the buyer continues here and continues in the second instance of the same behavior, and then he accepted the product and chooses the second product and then the second order, as while the buyer already waits for the timeout. And this can happen. So this composition is not a strict timeline, but the one part can already continue and the other is still in the old part.
Okay. This is the difference between the model and the instance. This is the difference between the model and the instance.
Yeah, this is reality. So I only want to model reality. Of course you want to have this kind of behavior. I only wanted to show this kind of composition is not entirely trivial. Because one part can already continue while the other is still in the old phase.
No, my comment is you don't need this complexity if you introduce the notion of an instance. Because each separate buy, if I want to buy something, it's an instant both at the seller and the buyer.
And then you have to prove that the different instances don't interfere. You have to prove that.
Well, if they are sound.
If
they are sound.
Yes.
Yeah.
It is not completely trivial that the composed instances are also sound. Because the instances are not completely independent. Okay. So the composition is sound too. So that means if you have this kind of a system and you compose it, and it is just the same figure again, this is the same second instance, so to speak, then we have the theorem composition of two sound services is again sound. That's what we wanted and that's what we achieved. Okay, then there comes a tricky property which I will not show you.
It's called?
Pardon?
How is it called? The tricky property?
We don't give it a name. Okay. And then I would have liked to show you how composition is very expressive, but I think I speak to this.
Still have 5 minutes.
Aha! Okay, then I speak about this. So now we have, again, this idea left part, right part, and compose them. So we have a provider and a request, a typical server situation. The provider is only a right part, and the request is only a left part, and we compose them, and this is a new system. Okay, that's what we have seen so far, and should not be any surprise. Now we do something very strange. We say the left part and the right part may contain the same element. So it's no longer really left and right. Now it's a same mathematical game. So what happens if you allow one component of the interface to be as well in the left port as well as in the right port. Okay? And that's what we do. We have a strange requester that has one element in the interface that belongs to the left as well to the right part of the requester. And now by definition of composition, and what comes out is the following. It will be composed, and the composed system has still a right port, and the right port is this. So this comes just from the definition. And how does it help? Well, if you have a second request of the same kind, you can compose it if we get this structure, etc. We can get this structure. So by simply writing p.arc, we get this kind of a structure. So now we can say in mathematical terms construct a very rich kind of systems. And for instance, here we have, say, one provider with a lot of input ports, of right components, and we have one generic requester, and it has one element only in the left port, and but the other in the left as well as in the right port. And we compose them, then we get this system, and we have a second this kind of requester, we get this system, and the third one gets this system. Okay? So then we can say, at least formally, construct with simple composition terms very rich kind of a structure. For instance, if we continue, if we want to have this kind of a system, just extend the right port by an A. If you prefer this kind of a system, just make this also an element of L. So this shows you that this composition operator has a lot of formal additional behaviors which have not an obvious interpretation, but I'm sure they can be used for something reasonable. And then we can get an algebraic structure of all this. So what are we given? We have given a set of things we call services. We have a composition operator. We have a set of requirements or properties. And this is a very well-known kind of algebraic structure. One set of elements, one binary as composition operator, one set of compositions. And of course, we want to have it associative. That's what we wanted from the stretch. And this is the kind of algebraic structure that we should consider.
Okay. Question. Why don't you need, so it's a simple algebraic structure. What trying to turn it into a group? As a neutral element inverse.
Yes.
Because sometimes if you compose, you want to decompose, so you outsource work and you have to insource.
Very good question. Is there a neutral element? And the answer is yes, there are. Unfortunately, not only one, but many. There are neutral elements.
What about inverse? Because in practice, inverse element.
Oh, inverse is no. Simply no. You cannot have.
Yeah, but this is in fact so. You have two orchestrators. You have a process. You split it apart into two processes because you outsource it. You have a lot of it. And at the end, you want to insource it again.
No. You see, if I send you money.
Yeah.
And you got the money, you took the money, I cannot undo.
Oh, in practice you do compensation.
Yes, you have compensation, but that's not much more difficult.
But it needs to be folded in.
I agree. But compensation is not just undo, it's not just a reverse. Okay.
No, there must be an inverse. It's not undo, it's an inverse.
Yeah, I agree to ask this question for compensation is a good question. Yeah. So you can. Of course, I say this is maybe the fundamental structure, and now you start asking all these questions to make it more rich. Okay. So this algebraic structure has a lot of things that you can consider. For instance, the notion of a partner that fulfills a kind of properties. So we say for two services and the property, we say T is a partner of S with respect to this property if the composed system meets this property. For instance, the property of soundness. Okay? Then you can say the semantics of a service is the set of all its partners. Okay? And the classical environment is soundness or recombination. And we can derive notions such as when can we substitute one service for another one? If the semantics of the substituted service is the subset of the semantics of the new service, etc. So a lot of questions. Equivalence, you can ask when are two services equivalent, then they have the same semantics. When can you, an adapter, very important, what is an adapter of two services S and T? Well, who is an adapter if you compose all of the the three of them, then they need a proper room. So now you can